Hello again. In this short presentation, we're going to have a look at a follow-on to what was in number 3. This time we're going to look at a little bit about how we fit statistical distributions to annual maximum flood data series in order to estimate the magnitude of floods at different recurrence intervals. We're going to have a little bit of a look at the what the package FastTR produces in terms of results, talk at some length about how to interpret the output graphs and the data tables. If you remember what the issue is that we're looking at, we are taking flow data series like this one. We wish to estimate the magnitude of floods of different return periods, and we're using the annual maximum approach, so that in each January to December period, we identify the largest flood event that's taken place, one event per year. So in this data series, which is only 4 years long, we only have 4 data points on these graphs. And we're going to have a look at a slightly better example with a longer data series in a moment, but we can take the data, fit curves to them based upon the distributions, either log Pearson type 3 or Weibull, and estimate the magnitude of events of different recurrence periods from that. So the package we're going to use, FastTR, or Faster I suppose, is able to process and visualize river flow data very easily, and within the package we can fit the log Pearson type 3, P3 on some of the slides, and Weibull distributions relatively easily. There is more than one way to fit these complex distributions to estimate their parameters. The software does allow different methods to be used. We're just going to use one method in the practical work there. And we're going to focus a little bit here on interpreting the output plots, and we've made several of these points before in previous lectures, but as a reminder, remember that each data point is the largest flood in one calendar year, and we put these in rank order from the largest flood at the right through to the smallest annual maximum at the left. And it's only one event per year that is recorded. The different colours on the graph show different averaging periods, the 1-day values in red, and then 3, 7 and 30 days in purple. And as we increase the averaging period, the magnitude of those events goes down because we're increasingly combining high flow days with days that have lower river flows, and therefore the average discharges reduce as the averaging period goes up. We've got 21 years of data in this data set for the Bioas River, and that allows us to estimate the return period up to 21 years, probability of just under 0.05. If we want to estimate the 50-year or the 100-year flood, we therefore have to extrapolate from the data into this red oval area, and that extrapolation is dependent upon how well the distribution that we choose fits the data. So you can see in this plot we've got the log Pearson 3 and then the Weibull are here on the right. The lines show the distributions, and I think we could make a case that either the log Pearson type 3 or the Weibull is a better fit in this case. Statistically there's very little to choose between them. Note that the highest magnitude recorded event for the Weibull does tend to plot slightly above the line, whereas it's closer to the line for the log Pearson 3. And we might use the fact that these last few points are on the line as evidence as to why we should perhaps use the log Pearson 3 in this case. On the other hand, the overall fit for the Weibull in all of the above probability 0.5 floods is probably ever so slightly better than it is for the log Pearson 3. So there really isn't a lot to choose between them visually in this case. We also can interrogate the results table, and this allows us to estimate the floods of different probabilities, or indeed we can use 1 divided by the probability to get the return period. So here we have probability of 0.01, return period of 100 years. For 1 day events, the Weibull is suggesting 210.5 cubic meters per second. The log Pearson 3 is suggesting 291.4, quite a lot higher for the log Pearson type 3, based on the fact that this part of the curve is steeper than the equivalent part on the Weibull plot. Probability of 0.05 or a 20-year event, 149.5, 172.9. By the time we get to the 10-year events, they are much more similar, 121, 128. The 5-year event, 91.1, 89. So not much difference for these lower return period, higher probability events, but for the sort of event we might wish to estimate for design purposes, we do get quite a significant difference. Sometimes it's appropriate if we're dealing with something that's very high risk, for example, high risk infrastructure, electricity transmission station, for example, we might in this case choose to go with a higher estimate because we really don't want to take any risks with the infrastructure. On the other hand, we may decide which is better to use based on the statistics of the fitting of the two curves, and it really depends on the quality of the data and how well the distributions fit. In the catchment project, we've done a lot of work fitting those distributions to the data sets that Pammy is going to talk to you about in another lecture. Remember that we have mapped the Weibull in green and the log Pearson 3 in orange, with the circle size being proportional to the size of the 10-year flood in these different locations. We said previously that most of our fits are slightly better with Weibull than with Pearson. There are some log Pearson 3 distributions, especially in climate type 2. The map over here reminds us what the climate types are. Climate type 2 up the eastern coast does tend to show more log Pearson type 3 distributions. And remember what we said last time, that larger catchment areas tend to be Weibull. In the practical exercise, you will get to use the software, you will see some of the results, you'll also see some of the visualization of the results, and will be able to interpret for yourselves the performance of those different distributions in the curve fitting process.